We are ready for the mean value theorem. Here it is. Notice we give it the abbreviation MVT because it's so popular, kind of like intermediate value theorem back in chapter 2. In the initials MVT almost make it seem like it stands for most valuable theorem, but it's not. It's just the mean value theorem. Okay, what is the mean value theorem? So it turns out it's actually a smaller version of Rolle's theorem. There's only two hypotheses. I'll show you the rest, the conclusion, just a second. If f of x satisfies the two hypotheses, and they're the same first two as in Rolle's theorem, number one, that f of x is continuous on the interval, the closed interval, a to b, and number two, that f of x is differentiable on the open interval ab. If both of those are met, then here's the conclusion. There exists C in AB such that f prime of C equals f of B minus f of A all over B minus A. So what is that? Well, it's a little bit more than what's going on in Rolle's theorem, right? What is that, when you look at that right side, does that remind you of anything? And maybe it reminds you of the equation for slope. Let me just show you the logic here. So keep in mind, with hypothesis 3 gone, we're not specifying, we're not limiting to this to that the y values have to be the same at the endpoints. The y values are going to be different at the endpoints probably. So what is this all about? That's the slope of the line, like between, or you might say the slope of the line connecting the endpoints. So somewhere there's got to be a C between A and B where the slope of the tangent line there is the same as the slope of the line connecting the endpoints. Or you might say the tangent line at C is parallel to the line that connects the endpoints. And that reveals even why the name mean value theorem, when you think mean, think average, right? So this means the average slope of f of x on the interval. If we think of the slope of the endpoints, the line connecting the endpoints, that tells us the average slope of f of x, of the tangent lines, if you will, connecting those two. Let me show you guys in a picture. Two pictures, actually, help to make sense of this. Ignore this over here for the moment. I'll tell you about that after the drawings. Okay, so here we go. So we're going to say, all right, we've got a point A and a point B. Now the y values don't have to be the same, but it is going to be connected with a continuous differentiable function. So, what if I just do something real simple, just like a curve like that? So here's what the mean value theorem says. Somewhere between here, somewhere on this path, there's a tangent line that is parallel to the line connecting. So if we got the line connecting A and B, at some point the tangent line is parallel to that. You're like, well, of course, right? Like maybe, I don't know exactly where it is, but maybe right there, I don't know. There, that tangent line would be parallel to the line connecting them. So the slope there is the same as this slope. Now maybe the function has got a little bit more going on. So let me draw this one again, maybe a little more complicated. Let's mix things up. Let's put the y value of A up higher than the y value of B. And let's say, I don't know, maybe this like comes up and then down and then, so long as it's continuous and differentiable. Okay, so if we think of the line connecting the endpoints, something like that. then is there somewhere, along this path, at least one point where the tangent line is parallel to that? You think, well, okay, yeah, so maybe if we think up here, it's not going to be at the very top, but maybe a little bit further, right? The tangent line there, I think it should be a little bit further back actually, is parallel. And if we come down this way, maybe not quite at the bottom, but a little bit to the left, that tangent line will be parallel. And there's even a third one up here at the top. That tangent line would be parallel. So maybe you call this like the C1, C2, C3. And I didn't write that back here, but right underneath that one, that would be your C. So again, we're guaranteed for this to happen at least once, but it could happen multiple times. And kind of with those drawings, we can even connect it to Rolle's theorem. Rolle's theorem turns out to just be a special case of the mean value theorem. Right, in Rolle's theorem, we said that the y values of the endpoints are the same. Well, if f of b equals f of a, if those are the same, then what's going to be true of f prime of c? If your y values are the same, right, wouldn't that whole thing become 0? And so f prime c is 0. In all the lines we drew, that the slope of that line there was always straight across 0. Well, yeah. So I'm not sure how Rolle's theorem, why it even exists, because it's just a special case of the mean value theorem. But I suppose there's probably enough uses of that special case where it makes sense to give it its own name. Okay. Also, kind of back here with, the average slope. So if we were to think, okay, if we were just to connect the endpoints and get that slope, then if we were to look at all of the tangent line slopes all the way across, if we were to look at every slope along the way and take the average slope, that average would just come out to be the slope of the line connecting the two ends. And hence the name mean value theorem, like average value theorem kind of. Whew. Okay, that's a lot. I think you guys are probably with me at this point. What do I have over here before we get to the example? In the textbook, they don't write the conclusion the way that I did. Why they didn't do that, I don't know. They're going to write the conclusion of the mean value theorem like this. There's at least one value of c, there exists c in AB such that this, f of b minus f of a equals c f prime c times b minus a. It's the same thing. All they did was take the b minus a and multiply it over here, and then switch the left and the right sides. But why would you present it this way? That completely loses the sense that you're looking at a slope. The slope at one point is equal to the slope of the line. I'd have no idea why they would say it this way. So if you see that in the textbook, or if you see a question and it has it presented like this, immediately just divide this over here and think of it this way. That's what I would recommend. And don't get confused by it. Okay. That's a lot. So let's look at this example right here. So we're going to do one of these examples that is similar to the Rolle's theorem examples, but then we're going to look at some other cases and other sorts of things you might come across with mean value theorem. Okay, so here, example, does f of x satisfy MVT on the interval? If so, find C. F of x equals x to the third minus 2x plus 6. And the interval from -1 to 3. Okay, so we're going to start off the same way. Is it continuous? Is it differentiable? Does it satisfy mean value theorem means? Does it meet the two hypotheses? So, is this function continuous on -1 to 3? Hey, it's not a piecewise. So we can tell right away, yep, no problem. That's going to be continuous on the interval. Is it differentiable on the open interval, -1 to 3? Well, we take a derivative and think, okay, does that derivative always exist for that interval? Sure does. Never dividing by 0, anything like that. So it satisfies the mean value theorem on the interval -1 to 3. Okay, now let's find the value of C in -1 to 3 that would meet the conclusion. How do we do that? Okay, so mean value theorem said, I'll just restate it. There's a value of C where this. So we're just going to put the derivative right there, the derivative function, and then on this side, we're going to plug in the values of A and B. So it's, oh, well, I guess I didn't need to copy that. There it is again. Let's get rid of this. Better safe than sorry. Okay, so where we see that derivative, I'm just going to put in f prime of x, and we'll solve for x. It's a C value, okay? And then here, the b is 3, the a is -1, so we're just plugging those in each place. And now let's start to clean up that right side. Put 3 back into the original function. The original function is there. All right, if we plug in 3, we get 27. I invite you to double check my work. If you put in -1, you get +7. So we've got 27 minus 7. And of course, in the bottom, it's 3 plus 1. So we've got 20 divided by 4. And here's what we're going to solve. 3x squared minus 2 equals 5. And we're just a couple steps away. Let's add the 2. Let's divide by 3. Let's take a square root. And here we are. Now, one thing to keep in mind, we do get 2 answers when we solve for x, but that doesn't mean that they're both in the interval. So let's pause for a moment and look at these one at a time. I'll just show you all of my steps here. So it turns out only that positive square root is actually in that interval. The negative wasn't. So if I break out my calculator here and go square root 7 over 3, and I've got to use my little double arrow to convert a fraction to a decimal. All right, 1.527, 1.528, whatever. Yep, that's between -1 and 3. But if we do the negative version, then of course it's not going to work. We're going to get -1.528, and that's no longer in -1 to 3. So that's not part of our answer. We can't include it if it's not in our domain for x. Okay, so this one was, this one's not. So we say, okay, ignore that. The only answer is here. Now at this point, we've answered the question, but I have a follow-up question just on kind of the conceptual side of things. Because that's always why not? Follow-up question. What is the slope of the tangent line at x equals the square root of 7/3? That x value we found here, that c, that was between -1 and 3. What is the slope of the tangent line there? And if you remember, well, the slope of that tangent line is going to be parallel to the slope of the line connecting the endpoints. or I should say the slopes are going to be the same. The lines are parallel. So what's the slope of the tangent line at x equals square root 7/3? And you'd have to go back to some work we did earlier, back over here. What is the slope of the line connecting the endpoints? And well, this is us calculating it, and it turned out to be 5. The slope connecting the endpoints. And so what is the slope of the tangent line at x equals square root 7/3? It's 5. So just so you kind of have an understanding of what you're doing and why, and don't just memorize a formula, but kind of while you're going through it, like think of it like, oh, that's the slope of the line connecting. Okay, yep. So it's 5. All right, we're going to stop this video here. I got a couple more examples of other types of questions you might see.